You're watching Channel 30 for all your Group 30 news and information with your host, James McInnes. And today, with a special report, here's James McInnes. Good afternoon. My name is James McInnes, and I'm reporting live from the Channel 30 newsroom here in Salem, Oregon. Today, we are bringing you a special report about a new product that was designed by the creative students at Oregon State University. Matt Cook, Kyle Macwood, and James McInnes formed the group known as Zero Dark 30 and have put their collective minds together to create an aid for pilots everywhere in the NAV 2000, sponsored by VAL Avionics. In today's special report, our man on the street, Kyle Macwood, will be interviewing Matt Cook, one of the student engineers who participated in the design of the NAV 2000. With no further delay, let's go to Kyle.
Thanks, James. I'm here with Matt Cook, one of the student engineers who designed the NAV 2000. We're here in the lounge of VAL Avionics. Welcome to our special presentation, Matt.
Thanks, Kyle. It's really good to be here.
To start off, what did you make?
Well, as a group, we created an aircraft navigation system, and our purpose for this project is that by using a combination of analog and digital systems, we're able to create a device that reads the highways in the skies. In addition, this device is able to read the runway landing systems in low visibility and automated landing systems.
That sounds complicated. Can you break it down so that our viewers at home can understand?
Of course. Well, here's the unit, and here we go. And as you can see, this is a solid piece of aluminum. It starts as 1.5 inches thick, and with a CNC machine,
That's heavy.
Using a CNC machine, we're able to etch away 90% of that material, creating a very good base for our circuitry. Now, this has an added bonus of meeting our temperature requirements required by the FAA, as well as containing the radio signals that might be emitted by the internal circuitry. Looking deeper into the unit, for the folks at home, I have here a basic block diagram that shows the key features and components within the unit. Starting with the antenna and receiver, the multitude of broadcast signals bombard the receiver, which separates and decodes the desired signals.
Signals? You mean there's more than one signal going into this at a time?
Yes, Kyle. That was a tricky bit of engineering. We combined two separate receivers that were on one board. This reduced the size of the unit while increasing the density of components. We were afraid it wouldn't be able to receive distant signals with extra noise that can happen with two receivers. But due to the aluminum case, the problem was resolved with no real difficulties. Remember, kids, shielding is your friend. Next, these two video signals go from the receiver and transition to the converters. Now, the converters are where half the magic happens.
Magic? What do you mean? And what are you talking about, video signals?
Well, not really magic. These two signals are filtered and cleaned up to isolate just the data that we want. Once the data is clean and tidy, we transfer it to the CPU, where the chief programmer, James McInnes, is our expert. Now, you can speak with him in just a moment. Now, as for the video signals, the reason it's called video is that the information that is provided, once it's all filtered and presented to the pilot, gives them directional information through a visual manner, hence video signals.
So that covers pretty much everything about the hardware unit of the unit?
Pretty much. I could bore you with some more high-level detailed stuff, but that would go over a lot of the viewers' heads, but that pretty much covers the hardware.
Thank you, Matt. Next up is James McInnes, chief programmer, who will discuss how the software takes the tidy signals and give pilots information to land the aircraft. So welcome back to our special presentation. I'm still here at VAL Avionics Lounge, and with me now is James McInnes, the chief programmer of the NAV 2000. I'm glad that you could join us here today, James. I understand that you have a very busy schedule.
Yeah, so you have questions about the software?
Well, yes. Matt mentioned that he worked with the hardware to clean up some of the signals that are going into the CPU. Why is that?
Well, obviously, it is there to make the system function better. Through having a small piece of hardware, the overall complexity of the whole system was significantly reduced, especially on the software side of things. Really, by working through the entire system and working closely with the hardware and the software, we were able to have the smallest system available. No need for expensive CPUs that do everything, and no need for a complete hardware solution that will have parts that go obsolete.
So what all does a CPU do?
Well, to be completely honest, it is the heart of the system. I mean, not to toot my own horn, but it controls the receivers, shows what frequencies are being received, takes the user input and translates into commands such as the frequency swap, memory, other functions along those lines, controls the volume, and it also controls the needles on the pilot's visual display. So pretty much the whole enchilada. One could say that it is the mediator between the user and the received signals.
So what was necessary in putting all this together? What was required?
Well, for requirements, goodness. The FAA has a bunch of rules that they require for an item to be considered airworthy. As we were students, well, we are students still right now as the time of this recording. So first off, our first test was really for the audio of the system. The navigational tones are intermixed. Well, to be completely honest, the video signals that Matt mentioned earlier, they are right in with the audio that a pilot listens to. So we had to filter that out. You don't want to be listening to those noises back behind when you're trying to understand what the VOR station is saying to you. The unit had to be compatible with the Garmin SL30, and that was just majorly getting a hold of some serial commands, implementing them, and testing them. The unit has to be compatible with the existing composite heads. So the old needle type displays that are out there, has to be able to drive them, give needle indication, and that way pilots don't have to reinvest in another expensive head. Do you know those things cost over $2,000?
Holy cow.
Yeah, that's more than twice the cost of our unit. 4, moving on to some of the internals, the glide slope system. That's what controls an airplane vertically when it's landing. The glide slope system has to be accurate down to minus 76 dBm. That's about 3 bars on a cell phone between you and me. As well, considering that you're landing an airplane, you don't want it jumping around, so it has to be linear. So no stair-step type steps between different settings. So it needs to be linear across the entire display. That was our 5th requirement there. So the localizer, requirement number 6. The localizer has to be accurate down to minus 79 dBm. Now that's only 3 dB of difference from the glide slope, but that is half the power. Although in our testing, we've seen it go down to minus 110 dBm, which is less than 1 bar on a cell phone. You'd be dropping calls with what we're landing planes on.
That's impressive.
Mm-hmm. The localizer also needs to be linear across this display because, like I described with the glide slope, you don't want it jumping back and forth. Then, let me see, number 8 was, that's right, it needs to operate and be accurate in up to 90% humidity. That is a hot summer day in Georgia. It is hot, it is sticky, we have a temperature chamber, we stuck it in, and we ran it through those tests, and oh, it was nasty.
Ew.
Oh, yeah.
Imagine.
Yeah. The VOR system, that's what allows you to fly on the highways in the sky. By the way, this is requirement number 9 out of 10, so we're almost through it. It has to be accurate within 3 degrees down to minus 93 dBm. And the last requirement, number 10, is that the unit has to meet temperature requirements. According to the FAA, it has to go from minus 30 C to plus 55.
That's a large range.
Yeah, pretty much. Oh, and again, the NAV 2000 met all 10 of these requirements. So, do you have any other questions?
Not really, but thank you for your time and for the explicit explanation. And now back to you, Matt.
Thank you, Kyle, for that in-depth report. Now that you have an idea of how the unit was put together, let's go on site with Kyle Mackwood to see a demo of the NAV 2000. Over to you, Kyle.
Thanks, Matt. I have here a NAV 2000, and now to answer the important question, how do I use this? Well, The design of the NAV 2000 is similar to a 50s car radio. You have your volume and power control on the left knob and tuning on the right. Turning the left knob, the volume shows up and gives a number showing how loud the audio is. And if I push and hold the button, the unit turns off. How convenient. Now, if I push and again, and you can see the unit turning on and starting up. Notice how quickly the NAV 2000 is started and ready to use. You can see as I am adjusting the tuning, the numbers on the right are changing. This is the standby channel, so you can change a frequency without having to go away from your main navigation frequency. And with the push of the button, the two channels are swapped and the channel I just entered is now active. If I push the left button, the unit accesses its channel memory, where you can set up to 15 frequently used stations, so you can instantly swap between them. Now, you may have noticed when I shade the display, it gets a bit dimmer. This is no trick of the camera. The unit is designed to change the brightness according to the available light. Having demonstrated the main functions of the NAV 2000 and how to operate it, I will show you how it operates in the sky. Not many people have taken a table to 30,000 feet, but today, I'll do it. For those of you in the Pacific Northwest, you know this is a map of Oregon. Here's Corvallis, and here is Eugene. This dotted red line is one of the highways in the sky that gets the pilot to his destination. Each destination has a certain frequency and radial. That's an angle to you and me. That is sent out by selecting that frequency and radial. You can stay on the highway in the sky. The VOR system will guide us to the next point for the highways in the sky. You can see here that if you are off the path of the highway in the sky, the needles will indicate which direction you need to fly in order to get back on track to your destination. Upon arriving at your destination, we'll swap over to an ILS frequency so the system can guide you to the center of the runway and land you safely. Landing safely is probably everyone's biggest concern. Now that we have arrived at our destination location safe and sound, you can go and party. Now back to you, James.
Let's recap what we've learned about the NAV 2000, sponsored by VAL Avionics. You've heard about the overall design philosophy. In this you saw the robust, sturdy case. We've talked about the 10 engineering requirements that were met. You've learned about the heart of the unit, which is the CPU that was programmed. You saw the aircraft navigation system guide you through the highways in the sky from our demo of the NAV 2000 as well as landing. I hope you've all enjoyed the overview of how the NAV 2000, sponsored by VAL Avionics, operates. We would also like to take this moment to give all future seniors some recommendations in order to have a successful project and not be overwhelmed throughout their senior year, which realistically most seniors would like to spend relaxing. Anyway, first we feel you should have a diverse team. Find at least one person with a CS minor, that's computer science between you and me, to help with all the coding that you're going to be doing. And even though you think you might not have a coding project, you will. There will be a microcontroller. 2, stay on top of all your paperwork from day one. If not, at least try and stay ahead of the game, because if you don't stay ahead of it, you're going to have a bad time, and you don't want to do that. This will help alleviate some of the stress that you will incur along the way. 3, Google is your friend. You can find everything you need to know by just Googling it. I mean, this is how we accomplished nearly every task we had. When it comes to designing your system, make certain that you have at least 10 to 30% extra in your power supply. Oh, speaking of power supplies, don't run parts at their maximum limit. Even though the status sheet says that it will run at 3 amps, don't try to run it there. Run it at 2 amps, test it at a little bit more than 2 amps, you'll be much happier. Also, realistically, make certain you have a creative person, someone who's an artist, and perhaps a marketing guy. You may not think you need those type of people for an engineering project, but come the last term of senior design, you'll be glad you have them. If you stay on top of any of these recommendations, you'll reduce your senior design stress and enhance your enjoyment. Because after all, that's what this is about, is having fun, not so much about anything else. And now, back to you, James. That was a great story. Thank you. Well, that's all we have for you today. And from all of us at Channel 30 News, I'm James McInnes.
I'm Kyle Mackwood.
And I'm Matthew Cook.
Thanks for watching. You stay classy, YouTube.